Well, I will share my. Welcome, everybody. I'm Dave Wanik, and I'm an associate professor in the Department of Operations and Information Management. And today I'm happy to give you one of my master classes on neural networks from scratch. So give me a second to share my screen, and I'll tell you all about myself and what I do. So let me see. I should be able to share here. Let's see. Can you all see that presentation?
Yep, but it's the presenter view, not the full screen view.
Oh, geez, that's cute. Because I've got the full screen view. Um, Let me see if I can switch that around. Oh, I see what the problem is. I should be able to share a different screen. So this one. How's that looking?
Perfect.
Excellent. Well, welcome everybody. I'm so glad that you're here. I'll give you a little rundown of what we'll do today. I'll introduce myself. I'll walk you through a common data set that we use in machine learning and deep learning. I'll show you how a neural network operates from a very simple uh, network architecture all the way to advanced methods. I'll show you how to pass information forward, calculate an error signal, and pass that information backwards such that you update your weights and make a more accurate prediction the next time. I'll show you a toy example and then a real data set, and I'll show you how a deeper neural network is able to learn more sophisticated nonlinear patterns and deliver a better result. Further, in 2026, you can't just fit a model and say, I don't know how it works. So I'll show you some model agnostic methods that work with neural networks and other techniques to show what was the most important feature, how did the model treat that feature, and even show you an easy way to use a neural network to get some type of probabilistic estimate of the thing you're trying to predict. I'll close with some cool pictures on convolutional neural networks and other architectures, and then I'll take any questions from you. So here's a little bit about me. I've been in the School of Business for 7 years. Before that, I was in engineering and I did a lot of utility energy analytics research in the School of Engineering. I teach a lot of different classes in the School of Business. I teach data science, cloud computing, deep learning, advanced deep learning, and every day is an adventure. The technology changes so fast, but the tools to engage with technology have never been easier to interact with. And so if you can get a basic understanding of these different methods, you really can start to fly and teach yourself as you go along, especially under the guidance of a professor like myself and those here at the University of Connecticut. I've worked with a lot of great companies. 15 years ago, I started my relationship with Eversource and Avangrid doing storm outage modeling. We created an AI model to predict storm outages in advance of a storm, and we licensed it to DTN, who supports research. Through UConn, I've had the pleasure of leading graduate consulting projects with Forbes and Lego and Control Station. And in addition to that, I also have active consulting with Harvard Steam Boiler, Munich Re, and I do a student-led experiential learning opportunity and decentralized AI with Yuma, which is essentially a crypto incentivized AI platform. So I wanted to show you some of the things that I like to do. So here's an example of some energy forecasting where I will use a neural network to take a time series of weather at the different airports in New England, and I'll predict how much energy is being used. And I'll also put the explainable AI piece on top of it and say, what's driving the prediction at this time step? Further, I got my background in environmental engineering, and so I'm very good with geospatial data processing, and I'm very interested in deep learning applications of GIS. And so here I have a satellite image of Hartford, Connecticut, and we're able to leverage building footprints to know where all the infrastructure is in the city. We can overlay that with other types of data sets like LiDAR that effectively give you a 3D mapping of the Earth's surface. And then I'll do things like high resolution population mapping in the United States and all over the world. I also do a lot of research on the impact of weather on critical infrastructure systems. So here is a cold snap that happened earlier this year, and you could see where there were trouble alarms going off for an insurance company as the storm progressed. So let's get to neural networks, and I'll show you that a neural network really is not that scary. If you can add, subtract, and multiply, you could do the inner workings of a neural network by hand. And it will really empower you and show you that you can do it. And if you could do it by hand, you'll be more adventurous to do it with code, and you'll be more excited to go after real world data sets. So I think a lot of you might know the California housing data set. We have 8 features for modeling that describe each of the different attributes in a census tract in California. We have the income and the age, the bedrooms, and we're trying to predict how much the houses are. So here's a bubble plot on the left-hand side, and you can see that I've color-coded the uh, the centroids of each zip code by the house price, and the bubble size is a function of the population. So you can see where the populated areas are and if there's a relationship between house price, income, and population. Here's just another exploratory plot, but I'll keep moving to keep the pace. So what I'm going to show you here is that we will take the first row of this data set, and you'll see the first row here are in standardized values of income, population, and rooms. You see the scale is different for each of those features. And so we're just going to subtract the mean and divide by the standard deviation so that we know that for this census tract that we're trying to predict, the income is really high. It's 2 standard deviations to the right, 2 positive standard deviations. The population is a little bit smaller, and the rooms are a little bit bigger than average. And we're trying to predict the house prices in hundreds of thousands. And so here, since the data has a limited range, I left it as is, and I'm not going to scale the target variable. But we did scale the input data, and that's really important because there's a whole host of math here that you have to be familiar with. And you'll see that if your input data is wild on different scales, so one column has a really limited scale versus one has a really big scale, the weight updates are going to crash your model and it's never going to fit. And so I'll show you, here is the simple network. This is what everyone thinks of when they think of a neural network. You have an input layer, you have a hidden layer, and an output layer. And I have 3 different versions of how the inner workings of a neural network operates. And I'll try to cover them quickly to see which one resonates with you. So you'll see that you have this input layer. These are just the first 3 features of a row in the California housing data set. So this might be, the income, the population, and the number of rooms in the house. There is a weight matrix in the middle, which turns this 3-dimensional input, 1 by 3, into a 1 by 2 dimensional output. And then this 1 by 2 hidden layer is multiplied by a 2 by 1 weight matrix, which gives us a 1 by 1 output, which is the house price. So what you're seeing here is that you could take something that is 3-dimensional and squish it down into 2 dimensions, and then squish it down into 1 dimension, which is your output. And it kind of looks like this. This is the first row of the data set. Remember I told you that we scaled everything, 2.3, negative 0.97, 0.63? Well, these arrows on the plot are actually just a rectangle or a matrix of data. I try to make this as accessible as possible because if you go into the calculus behind this, I think you turn a lot of people off. Versus if you could see the geometry and the numbers and see how things literally add up across the network, you're going to appreciate forward propagation no matter where you are in your mathematical journey. So you can see, here's this first row of the data set. We do vector matrix multiplication, and we add a bias term, kind of like a linear regression. And we're able to turn a 3-dimensional input, 1 by 3, into a 2-dimensional output. And then there's a handoff between this hidden layer and the output layer. We multiply by another matrix. And so you have this 1 by 2 vector multiplied by this 2 by 1 matrix. plus a bias term similar to like a linear regression. And then we get our output. And so what do we see here as we're passing information across the network? Well, we see that our input of income, population, and rooms gets squished down into two-dimensional space. It creates this output. And that output, just skipping ahead with our numbers, that output is 1.6. So that means that our neural network underestimated. We are trying to predict a 4.5, and our model predicted a 1.6. So our model has underestimated. Calamity. So what can we do? We are going to update the model weights such that we make a better prediction next time. And in this example, I only have one row of data. So I'm going to show that this network architecture, which was initialized with random weights, will be able to learn a relationship between input and output by updating its weights. What does updating its weights means? It means that we are going to take the error from this model prediction and we're going to feed it backwards. And we're going to say that since our model underestimated, the positive weights in our model architecture have to get a little bit bigger. And that makes sense because we're passing information through the network. And if we make the model weights a little bit bigger, our prediction will get a little bit bigger. And the negative weights have to get a little bit smaller. If you go back to this example, you'll see that we have some negative weights. Some of those negative weights will get smaller. And I say some of them because if you do a negative number times a negative number, you get a positive. And so we will see that after one back pass through the network, we will update the weights and our error function goes down, down, down. And you can see that our neural network is able to memorize this row and error will go to 0 and it will have effectively created a neural network that can predict one neighborhood's house prices. But one neighborhood isn't good enough, right? So yeah, if you have a small network architecture in one row, you'll memorize that thing. Then I gave the neural network 5 houses to memorize. And you could see that, to generalize a network architecture to minimize error and predict house prices for 5 houses, it takes longer for the model to learn. How about 100 houses? Takes even longer to get down to this 10 to the negative 1, right? It takes almost 500 epochs versus about 80 epochs for the model to get there. But that was a toy network. I tell my students that building a neural network is a lot like building a cake. And so you are going to build different layers of the neural network, much like you're crafting a cake in the kitchen. And you have flexibility to choose how many layers and how big those layers are. So this was our toy example, and I'll keep it on the side just to show you that this small network architecture is too small. We're trying to cram 10,000 rows and 8 features into this neural network, and it's going to bomb. Versus a deeper neural network, which has a few hidden layers, you see that our input will go through 3 stages of nonlinear transformations before it gets to the output node. And by doing that, we are able to better learn different patterns in the network architecture. And I'll show you that both of them both look kind of good that they're learning something, but when we tease out the actual performance, that small neural network bombs. It's not able to predict anything in the 0 to 1 range. And in these actual versus predicted plots, you want to hug this unity line, this 45-degree line that goes diagonally across the image. Our deep neural network is able to learn the relationship between input and output. And it can say things like median income and population and house age and all of these other features are useful for predicting house price. And we actually get a good predictive model. This data set is famously censored at the extremes. Anything that was greater than $5 million has been clipped to 5 million. And so that's why we see such a challenge here at the extreme of our prediction interval. But it's not enough to get a good model, right? I have code examples here for all of you that you can go and play with this example. It's not enough to say, hey, my R squared is better, my MAE is low, and so I'm done. I'm just going to ship this model and put it away. No, you have to tell your boss why you got the results you did. And that's this whole field of explainable AI. And so there are three things that I like to do with my students. The first is permutation importance. And what you do is you take this calibrated neural network and you show it a test data set that looks like the data set it was trained on. And what you're going to do is you're going to corrupt that data set very deliberately. What you're going to do is you're going to take that first column and you're going to shuffle it in place. And so your trained neural network is going to predict a little bit of a dirty data set where that first column has been shuffled. And if you're still able to get an R squared that's really good after shuffling a column of data, that means that that feature may not be so important. Versus, as you would expect, if you shuffle another column like latitude and the R squared value goes to zero, because now you've broken all the patterns in the model, all the relationships, then that's a really important variable. So at a global level, we could do this. And since we could shuffle a column in place infinite numbers of times, this is usually called repeated permutation importance. And you'll see that things like latitude and longitude are really important. Where you are in California drives your house price. So does your income. We can also say, how did the model treat those features? And so what we do is we take each row in the data set and we feed it a different flavor of each variable. We actually feed it each of the percentiles of the distribution. And we could see that as latitude values increase, house prices decrease. Same with longitude, but you can see there's a nonlinear pattern. And you can see that as income increases, house prices increase, but after a certain point, it kind of plateaus. And the way that this is made is that each of the 10,000 rows in our data set is fed with those 100 percentiles of the distribution, and it makes one of these gray lines. So it's almost like the journey of each row. And then you take the average of all of those 10,000 rows in your data set, and you're able to generate the average response, the marginal response. Further, you can even do something like SHAP, and I don't have time to go into SHAP in full details, but these methods are largely off the shelf, and you can interrogate your model and say, how did the model make its decision? How did it come up with 2.62? And it says, well, latitude is adding 1.57 to the house price, longitude subtracting it, so they're kind of fighting each other. And then it's the average rooms and the income that are largely influencing the prediction. And further, why I like a neural network versus other methods is its flexibility. You know, I already told you that I told my students that building a neural network is like building a cake. Well, you could use dropout during training to emphasize different parts of the network. So you're actually turning off random connections in the model's brain, and that helps the model emphasize different regions while it's learning, and so you get a more robust prediction. But it turns out you can also do this when you're trying to make a prediction, and you can generate 30 realizations of a single prediction as the model's going along. And so you get a histogram, you get a probabilistic output from your neural network. And so no longer do you have to give a point estimate and say, my model said the answer is 1.8, and you're very confident. Instead, you can use dropout during inference or the testing phase of your model. You generate this distribution of outputs, and you can say, hey, my model seems to be very confident. Or if you look over here, it goes from -8 to +8. And you could say, my model's very uncertain for this row. So even though I'm testing this new house and I've got this point estimate, the interval is so large, maybe I need a human in the loop to check it. And lastly, I just want to say that, you know, if you can see the forward pass of information, the calculation of the error, and the back propagation of the error, then all the other network architectures, whether it's for images, time series, videos, or text, there's just a little bit of knowledge that you need on reshaping the data and the different network architectures for you to leverage neural networks for these different unstructured formats. So images effectively get transformed into something that looks like that final hidden layer in a dense neural network, and then it's just recoded into some output. And so if you're comfortable with predicting house prices and you're really able to grab onto this intro example, text, time series, images, video, audio are all just waiting for you. So neural networks aren't really that scary. They're just a nonlinear weighted sum of information, and they aren't unknowable. we have the XAI that we're able to do to say, how did the model make its decision? And further, data processing and structured and unstructured data, that barrier to entry is coming down. And the large language models are really helpful for helping you prepare your data for these advanced network architectures. So once you're able to predict house prices from an Excel spreadsheet, the world is your oyster. And you're able to look at all different types of unstructured data. You just need to use a different neural network architecture. So with that, I'll pause. It's a lot of information, but I hope that I've convinced you that neural networks aren't that scary. And I've got the code here for anybody. If they'd like to go run the Google Colab notebook, you're welcome to try that out. And of course, I'm always here if you have any questions. So let's open it up. Who's got a question? Matt.
Hi, Dave. Sorry, little technical issues. Can you see me or hear me?
Yes, I can.
Awesome. Um, is there a data set size below which you would not want to use a neural network?
Generally, I think the gut feel would be I'd want like 1,000 rows in a data set, just because I feel like that gives the model enough meat to chomp on. But even beyond these simple networks that I showed you, for the advanced architectures, if you only have a couple hundred records for the problem that you're trying to solve, you're actually able to pull these sophisticated state-of-the-art models off the shelf and fine tune them. And so if you are data limited and you only have a couple hundred real samples of the data for the problem you're trying to predict, you're able to leverage these state-of-the-art models. And so small data is less of a problem today than it was 10 years ago.
Wow, cool. Thank you very much.
Thanks. I'd like to hear from some prospective students. What did you guys think? Have you worked with neural networks before? Have you seen it presented this way? It's always tough, showing folks or doing things and not being able to see people's faces all the time. Other questions?
Just a
Has anyone?
reminder, you can type in the chat your question, or you can unmute and ask your question verbally. Both are okay.
Yeah, Dave, you might want to check your direct messages because I put my question in and it went direct to you and maybe you missed it on the chat.
Sure. Is anyone afraid of coding in Python? Is anyone a proficient or an expert Python programmer?
I'm afraid of coding about of Python.
You're afraid of coding with Python?
Yeah, since I'm just a beginner.
Yeah, you know what? It's never been easier to uh, learn a coding language, though, right? The way that I like to teach programming is that I teach the syntax basics to get folks comfortable with data formats, data structures, variable names, but then I have them immediately do the things they would do with Excel in Python, and that helps students see that wow, Python or any other language like R or Go are really useful for scaling your idea. And it's also really useful for auditing because once you code something up, again, using the analogy of cooking, you have the recipe of what you did. And if you want to make a change, it's really easy to edit it. So we have a Python bootcamp that we offer all incoming grad students. And
Yep.
in that boot camp in a 3-week period, you'll see that most of the things that you do in Excel, you could do in Python faster. And that really gets students supercharged and ready for the semester.
Yeah, thank you. I had
Yeah,
another question when you were talking about neural network and concerning the energy sector specifically, like in the oil and gas. can we apply neural network in the oil and gas for real-time data? Because that is one of my main concern because I have a master's in petroleum engineering and I
Mhm.
wish to apply neural network like for drilling optimization or reservoir engineering in oil and gas. So I don't know, is it possible to do that?
Absolutely. We'd have to talk more on your specific use case, but whether your data set is more transactional or a time series or an image, a neural network could be a helpful tool to do some forecasting. And there's this whole other area of physics informed neural networks that could help with the physics to make sure that you obey first principles and such. And I work with a lot of engineers in my classes. I come from engineering and I teach in the business school now. And I think engineering gives you a really strong mathematical background to thrive in business and data science.
Okay, thank you, Prof.
Yeah,
Nice to
thanks for
know
coming.
you.
Sounds good. Anybody else? Is anyone else interested in explainable AI? Or is anyone else excited to try a neural network on their data set? I know it can
Um,
be. Oh, yeah, welcome.
I'm seeing Matt Samuelson have raised a hand somewhere there.
Matt Samuelson. Oh yes, yeah, but he was able to share previously, so I'll lower his hand.
Okay.
Anyone else have a question they'd like to ask? Well, I thank you all for coming. If you have any questions on neural nets, I have my code here, and I'll just click the link and share my example here. I like to teach with Google Colab in the classroom because it lowers the barrier to tech, and and so I could show you the code right here. If you want to try it out on your own, all of my examples are right here for you, and you're able to access them and just push run all, and this whole thing will run. And if you want to play with Keras, which is what I teach for deep learning, you can come in here and play with different variables. You could play with the neural network and add a bunch of dense layers and see if that improves your prediction. You could change the 2 to a 20 to see if that makes a better prediction. You could try to fit it for longer or shorter, or change the batch size so that you're just playing with the model directly. All this code is here for you, and you're welcome to grab it and run it and reach out anytime if you have questions. So I guess I'll stop for now.